All right, gentlemen. So I wanted to start we only got like a solid minute before class officially starts. I just wanted to like take a little bit of time before class starts, just to kind of check in. So give people a chance to like ask questions or something like that. Just to kind of check in. Sorry. So I discovered this, like, I don't know, I've been kind of like making my way through like different things on Netflix, and they're really interesting. Yesterday I found myself watching this movie called, and this is just shameless, promoting of other people, making other people rich. Like, this is one thing that kind of like irks me about everything. We talk about like just different things that are out, like social media and like entertainment and stuff like that. But when we do that, we're promoting other people's businesses and we're making money for them. I'm like, I don't know. I think the first thing for us to do this for ourselves is first we have to become producers. If we're not producers, and we're kind of discussing this stuff, if we don't have a line or a track for money to come in, then then the money can't come in. So it's like, if we don't have a product or something to promote, then when we do these kind of things, it's kind of hard for us to push our own product if we don't have one. But I see the time. But yesterday I was watching this movie called what is it called? The School for Good and Evil. I was like, okay. I liked it because it wasn't linear, right? Like, I can't stand it when things are predictable, and it's not that it had this great depth or anything. It had potential, and you could see where it could go so many different ways. But it was a little bit better than I anticipated. And the reason I started chatting about this today, though, is because before we all started, I was watching a show called Who's the Mole? So it's like, I think there's a game called Imposter Amongst Us or something like that. So you're like trying to figure out who's the mole. So on Netflix, there's a series called Who's the Mole. I'm like, oh my lanta. I'm on episode maybe like 2 or something like that. I'm just giving people a little bit of time to get in. As they trickle in, I'm kind of like, taking attendance and all that kind of jazz. Usually I do it in one go, but just trying something a little different. So, but I was like, well, maybe because I think there is a way that we can actually play a game like that. I think I know there are different versions of Imposter Among Us. I don't know what platform we could use. And just as like a team building, just something fun to do. Like, and I know we can do it. I don't know. One day I want to try something like this. So if anybody has ideas on how we can get as many people involved as possible, or like teams, and maybe, I don't know. I don't even know how I can tie it into what we talk about. Maybe if I could find a way to tie it in, maybe I can like, do something. But I think it would just be fun just to, like playing Imposter Amongst Us. I think there's a mobile version. I got to research there a little bit. Okay. I think I'm going to go ahead and get started. Let me share my screen, and I'll get anybody else that's late. I'll get them. Hang on. Go ahead. All right. So let me see. Anyway, it was just a little bit of brainstorming. It's something I kind of want to do. I'm sure there's a way that we can tie it in, because as far as I'm concerned, everything is a personification of mathematics. Everything can be articulated or expressed mathematically one way or another. But that's neither here nor there. Okay. So hope everyone enjoyed their weekend. Hopefully you enjoyed your homecoming. I don't know if anybody has any homecoming stories they'd like to share. I don't have any. I don't know. I guess through the years, I just kind of, you've been to a couple. Now, if I were a student, I would be going through all of it. Like, we have fashion shows, events, dances, balls, galas, the homecoming game. Did we win the homecoming game? Can anybody tell me? Did we even have a homecoming game?
Hell no, we ain't win.
Yeah, okay, that's I don't even know why I asked that question, because I don't remember the last time we won a homecoming game. like we don't be winning, but it's okay. That'll shift one day. But yeah, I can't think of anything else. Okay, so we are at the top of week 11. So you should know what that means. That means what? Next week we can anticipate exam 3. I think today we're wrapping up chapter 6. We're working on section 6.3 today. So that means I think I scheduled the exam to become available this upcoming Sunday. Usually I do it like Sunday mornings at 11:11. I think that's when it's available. I had to check my records or whatever, my schedule. But exam 3 should become available this weekend, like on Sunday. And it'll be due the following Sunday at 11:59 p.m. And that that exam should focus on chapter 6, so section 6.1, 6.2, and 6.3. And so today we're going to take some time and go through as much of the lecture for section 6.3 as we can. And then on Wednesday, we'll take some time to go through as many of the homework questions as we can. As usual, this is remote asynchronous. If you have questions, my recommendation is to unmute yourself to get my attention and we can talk about it. Else you can also type your questions in the chat. I do check the chat periodically. Okay. And I'll check Zoom again around the 15-minute mark to get anybody that's coming in late. So I kind of was stalling a little bit just to kind of get people a chance to get in earlier, and then I'll check it again around the 15-minute mark. So with section 6.3, we're going to be talking about geometric sequences in series, right? So I think this whole chapter, we've been talking about sequences in series. I think 6.2 was arithmetic sequences in series, and so we explored some concepts there. With arithmetic sequences, should I say, that's where you were basically adding the same thing each time. So we had this concept called the common difference, where we were adding the same number at each step, right? And then we saw a way to jump to any specific term in the arithmetic sequence. So geometric is similar. It's a similar concept, but instead of adding the same thing each step, there's only one slight twist, all right? There's one slight change, okay? So a few objectives here. We like to identify a geometric sequence and find its common ratio. We like to find the sum of a finite geometric sequence. We like to solve annuity problems and find the sum of an infinite geometric sequence, okay? So we'll get through as many of these concepts together as we can. Whatever we don't finish together, I think I did all the pre-recorded lectures, so this is already available, right? The stuff I'm about to say is already on my YouTube channel. There's a playlist that has all this already ready to go, right? I'm just filling in the air for right now. Okay, so let's take some time to get through this. So we have the definition of a geometric sequence. It says this sequence, let me grab, So this sequence given here is a geometric sequence or a geometric progression if there's a number R such that each term except the first term in the sequence is obtained by multiplying the previous term by R, right? The number R is called the common ratio of the geometric sequence. And R is going to be found by taking the AN plus first term divided by the ANth term. So one term divided by its previous will give you the common ratio, as long as N is greater than or equal to 1, right? So from the second term on down, you can take any of those terms, divide them by the previous term, that'll give you the common ratio. So geometric sequence is essentially the same concept as arithmetic. The only difference is instead of adding the same thing each time, instead of adding the common difference each time, now we're going to be multiplying the common ratio at each step, right? To find the next, okay? All right, I feel like that's simple enough. So here we're asked to find the common ratio. Let's go back. I don't know, sometimes this thing is temperamental. No, that's not it. This one. Okay, that looks better, okay. So here we're asked to find the common ratio for each geometric sequence. Okay, so I think we just said that to find the common ratio, you could take any term divided by the previous term. You just can't any term from the second term on down divided by the previous term will give you a common ratio. So for instance, notice that 10 divided by 2, I think that's 5, right? But then that's the same as 50 divided by 10. That's the same as 250 divided by, 50? So yada, 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 right? Notice that all of these, when you say one term divided by the previous, they all divide out to 5, okay? So that means our common ratio here is 5. All right. Okay, let's copy. Let's just undo. Copy. There we go. Okay. So we said we can take any term divided by the previous, except for the first term. So it looks like this one is what, a positive 1/3? Because if you said -2 divided by, I just chose the numbers that were more simple. -2 divided by -6 is 1/3, but that should be the same as -6 divided by -18, right? So on and so on. That should be the same as -18 divided by -54. Right, all of these should be 1/3. Okay. So our common ratio is 1/3. Okay. So what that means is that each step we're multiplying by a third. Okay, let's go to the next part. So we got 5 for part A and positive 1/3 for part B. Okay. So we've introduced this notion of a geometric sequence. So now we want to take it a step further and explore what do we mean by the recursive definition of a geometric sequence. So before, when we talked about the recursive definition of an arithmetic, is basically a definition that feeds back on itself. So it'll give you like maybe some initial conditions, and then it'll tell you how to progress or how to get to the next how to get to the next term in the sequence, right? So a geometric sequence can be defined recursively. The recursive formula, the n plus first term is going to be r times the nth term, as long as n is greater than or equal to 1, right? So this applies as long as you're talking about the second term on down, or actually the first term on down, because n could be 1, right? So this will give you like the second term, third. The first term is usually given to you, and then the subsequent terms are used. You use the initial conditions to find a subsequent term. This defines a geometric sequence where the first term is A1 and the common ratio is R. Okay. So determine whether each sequence is geometric. If it is, find the first term and the common ratio. Okay. So if we want to determine if this sequence is geometric, it's probably a good idea to list out a few of the terms, right? And look at it. So for part A, for instance, let me see, when n is 1, so the first term will be what, 4. Okay. The second term will be 4 squared, which is what, 16. The third term, 4 to the power of 3, what is that, 40 plus 64? Is it 256 is the next one? Hey, Siri, what's 4 to the power of 4?
4 to the 4th power is 256.
So on and so on, right? So, and it does look like we're multiplying by 4 each time, okay? So then our first term, we've identified it. So our A1 is 4. We already identified that. And then our common ratio, we're multiplying by 4 at each step, okay? Hopefully that's okay. So then for part B, let me see. So the first term is 3/2. Second term, 3/4. The third term is 3/8. Fourth term, 16, right? 3/16. So it looks like we're multiplying by what, a half at each step? So our first term is 3/2, and the common ratio, it looks like we're multiplying by 1/2 at each step. You know, don't take my word for it. I definitely make mistakes. So if you see something that looks weird, you know, bring it to my attention and we can talk about it. Okay. What's the time? About a minute and a half. Let me see. Times 2. Okay. And then for part C, let me move this over just a little bit. That's good. So then for part C, the first term when n is what? 1. So it's 1 minus 5 is -4. The second term, 25 squared. 5 squared is 25. So -24. The third term, 125. So -124. All right. Let's try to do one more. 625. So then -624. First we multiply by 6. But then 6 times 24, let me see, 6 times 2 is 120. Right? We're not multiplying by 6 at each step. Hey Siri, what's 6 times 24?
6 times 24 is 144.
All right, 144, right? So this one is not geometric. Let's do it like this. Give me a second. I'm just being a little bit OCD for no reason. And I'll check attendance in just a moment. That's fine. All right, so we got that one is not geometric, okay? So we got 4, 4, 3/2, 1/2, and not geo. Yeah, 4 and 4, you see it there. So the first term is 3/2, and the common ratio is 1/2. Okay, so we're good there. Okay, it's not geometric, right? Right here. It's not geometric because, okay. All right, so hopefully that's okay. Let me just take a moment. I'm gonna check Zoom. So yeah, like if you're ever late, you just have to wait, right? That's all it is. Like don't leave, just wait. Because I usually check it at 2. Even if you miss the 15-minute mark, still just wait because I'll check it again before I leave. And then just so you can get your credit. So you're not like, let's see. Student. This one. Okay. Yeah, there's some students I haven't seen in a while. I need to go through, sit down and go through and do some alerts because some students I have not seen. Like I was like, okay, I don't know where they are. Okay, hopefully everyone is doing well. Let me see. Let me share my screen. Chat looks good. So we're continuing. So if you're just joining us, we can anticipate exam 3 to become available this Sunday. I think I scheduled it for Sunday at 11 a.m. I think that's usually when I make them available. It'll be due the following Sunday, and it's over chapter 6. So today we're working on section 6.3 on geometric sequences and series. And geometric, no, I said, oh my God. Hey, Siri, stop. She's listening way too hard. Stop. So creepy. Speaking of creepy, this is something I just watched on Netflix. It's this movie called Jexy. Jexy is like, you see how Siri just started talking? Imagine if Siri was like sassy and like, all in your face and you couldn't escape her because she's like in the cloud or whatever. That's what Jexy was. That was entertaining as well. Anyway, that's on Netflix. Okay. So let's take a look at this. So we have the general term of a geometric sequence. So again, if you're just joining us, last time we were doing arithmetic sequences where we were adding the same thing each time. Today, what we're working on is this concept called geometric sequences, where we're multiplying the same thing each time. Okay. So suppose we wanted to jump straight to any term in a geometric sequence, then every geometric sequence can be written in this form. Okay, you have the first term, the next term is going to be that one times r, and then the next one is going to be that times r, and then that times r, so on and so on and so on, right? So the nth term is like this. Well, r is the common ratio. Since the first term is a1 times 1, which is r to the 0, the nth term of a geometric sequence is going to be given by, the nth term is going to be the first term times r to the power of n minus 1, where n is greater than or equal to 1, right? So if we wanted to jump to any specific term in the geometric sequence, we use a1 times r to the power of n minus 1, okay? All right. So for the geometric sequence, find the first term, the common ratio, and the nth term. Okay, so let's do this. Okay. All right, so the first term is given. So for part A, the first term, we can just look at it, is 1, right? Common ratio. So then for part B, common ratio, what are we multiplying? It looks like we're multiplying by 3, right? 1 times 3 is 3, times 3 is 9, yada, 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 right? Okay, so that wasn't too bad. So the common ratio, we're multiplying by 3 at each step. So then now for the nth term, that's going to be the first term times r to the power of n minus 1. So then that's going to be 1, and our r is 3 to the power of n minus 1. Can we just leave it like that? I don't see why not. So it looks like the nth term is going to be 3 to the power of n minus 1. Okay, and we can verify that this works, right? So for instance, when n is 1, 3 to the power of 0 is 1. That checks out. When n is 2, 2 minus 1 is 1. 3 to the 1 is 3. Okay. When n is 3, it's going to be 3 squared is 9, so on and so on and so on. Okay. Let's do it like this. Just to be clear about answering the questions being asked. Okay. So the first term is 1. Find the ratio of any two consecutive terms, which is 3. So the nth term is going to be 3 to the power of n minus 1. Okay, that wasn't too bad. Oh no. Oh shoot. That's not supposed to be on display like that. Okay. I'm gonna improv because I want to try this one. I know we can see the result here. I'm gonna drop one here. Oops. Let me get rid of this. Get rid of this. That's all I want. You can drop it right here for right now. And then I'd like to add a page because I want to attempt this. Oh, let's do another thing. See, that was my hesitation. I might have to like, give me a moment, guys, because it kind of throws a tantrum whenever I try to do this. I'll be right back. I know you can't see my screen, so just give me a moment. Did I lose my image? Looks like I lost my image. Okay, that's fine. Ugh. I don't understand why it does this. So like what I'm trying to avoid is to have to restart my device. That's what I had to do last time for it to work. Let me just try it again. I want to add a page. There we go. And then I want to leave it like that. Templates. Right. Here it is. apply. This one. Okay. And I think that's good. So I guess when I was preparing the notes, I just missed that slide. Okay, that looks fine, I guess. That's fine, okay. I don't like that. I'm coming, guys. I'm just trying to position this properly. We're gonna work with that. Okay, that's fine. And okay, that looks good. Let me share my screen. Okay. All right. So I didn't want to just skip this. I wanted to give it a go, right? So I think we, the answer was there, but it's fine. So then we're asked to find the 23rd term of a geometric sequence whose first term is 10. Thank you. Stop. Whose first term is 10 and whose common ratio is 1.2, right? So a moment ago, we said that the nth term of a geometric sequence is going to be given by the first term times r to the power of n minus 1, right? Okay. We have the common ratio, we have the first term, so I think that's pretty straightforward. So then if we want the 23rd term, first term is 10, common ratio is 1.2, and n is 23 minus 1. So then we just crunch those numbers. Okay, that's clear. So we're just going to say 10 times 1.2 to the power, I'm going to just do 23 minus 1, right, or 22. Okay. We'll do 4 decimal places. 52, yeah. 552.0614. It didn't specify how many decimal places. So for this one, it was really just a calculator problem. Okay. Let's, now we have the type version here. See, we got 0.06, so that's the same thing we got, right? Okay. All right, so sum of the terms of a finite geometric sequence. So finite means it ends somewhere, right? It doesn't go on forever. So let this sequence be the first n terms of a geometric sequence. That means we're multiplying the same thing each time, where the first term A1 and the common ratio R. Then the sum S sub n of these terms is going to be given by this. Now, this is the Greek letter sigma, just like in fraternities, right? But in this context, this symbol means summation, right? It just means add up those terms, right? So this says if you add up the first term, the second term, the third term until you get to the nth term of this sequence, let's see, it's going to be given by this. Let me see. Okay. I want the same. So when we did something like this for arithmetic, I was able to derive and show you where this came from. I want to try the same thing here. Hopefully this doesn't like disrupt everything again by trying to add a page. Okay, it's looking okay. Okay, so let's see if we can derive that. Again, you don't have to know this. I'm just doing this for my own sake, just because I want to give it a go. Okay, see if I can remember the trick. So we're considering a geometric summation, right? So let S sub n be the sum of the first n terms of a geometric sequence, right? So then we're going to have the first term plus, now let me think about it. The second term is going to be what? The first term times R, right? And then plus the third term is going to be the first term times r squared. And then the nth term is going to be the first term times r to the power of n minus 1. Okay. So that's the sum of the first n terms of a geometric sequence. So then now let's consider another summation where we're going to take that same summation, but now we're going to say r times that sequence. So if we distribute r across, then the top one turns into a1 times r plus a1 r squared plus a1 r cubed. And then when you get to the nth term, it's going to be a1 r to the power of, I think it's n, right? So all I did was take that first one and multiply it by r. So now we're going to do a technique to cancel out a lot of these terms, right? So what we're going to do, we're going to say that first summation minus, we're going to subtract the second summation. So essentially, we're going to distribute a negative across all of these guys, all right? All the way across. So we're going to say the first one minus the second one, okay? So if we say the first one minus the second one, then we're going to have Sn minus r times Sn, okay? Now what happens when we subtract, when we say the first row minus the second? Notice this a1r is going to be canceled by this a1r. This a1r squared is going to be canceled by this guy. I think everything cancels. Only thing that's going to be left is the first and the last. Right? Okay. So the only thing that's going to be left, we're going to have a1 minus a1 times r to the power of n, right? Now on the left-hand side, we can factor out that Sn, right? So if we factor this guy out, we're going to have 1 minus r. On the right, we can factor out the a1. We're going to have 1 minus r to the n. And now if we want to get an expression for the Sn, just divide by that 1 minus r. So that means the sum of the first n terms of the geometric sequence is going to be given by a1 times 1 minus r to the n all over 1 minus r. Right? And that's where this guy comes from. That's so much fun. I don't know about you guys. I know it seems like a mindfuck, part of my French, but that's fun. Like, and so like, you know, I came across that a few years ago working with you all. And so I like to just make sure I keep it in my psyche, like I still know how to derive those. Like in math, what you'll discover is a lot of these formulas, when you're able to derive the formula, you actually get way more. Instead of just remembering some rote memorization of some random formula, if you know the backstory, this is the backstory on where it came from, on the thinking. You know, we did something similar for the arithmetic, right? We derived the formula, we show where it came from. So when you're able to derive the formula, not only does it give you formulas, but it leads into other formulas, like, and other ways of thinking. We took this finite sum, and through these manipulations, we were able to generate an expression for the sum of the first n terms. And I think we got exactly the same thing, right? Okay. So that was interesting. You don't need to know all that backstory. I was just doing it for my own sake, and so you can see where it came from. Okay, let's move forward. Let me check on you guys in Zoom. Hopefully we're all aboard and we're not all bored. I know this stuff is intense, but I just realized where I heard that from too. But it's just oh, come on. When you're doing presentations, if you want your audience to have fun, you need to have fun, right? On some level, on some degree. Anyway, okay. So finding the sum of terms of a finite geometric sequence, find each sum, right? So we have the sum of the first 15 in either case, okay? I think we just got an expression for the sum of the first n terms. So we just said Sn for geometric, let me think about it. I think it was A1 times 1 minus r to the n over 1 minus r, right? Okay. So if we can identify the first term in the common ratio, then we could just punch it into this this formula, right? So then for part A, our first term, so when the first term, let me see. So basically when I is 1, it's like the output is what, 5? Because this is going to go to 0. 0.7 to the power of 0 is going to be 1 by definition. And then 1 times 5 is 5. So it looks like our first term is 5, okay? And then I think at each step, we're multiplying by 0.7. Let me see, when I is 2, yeah, we're multiplying by 0.7. Yeah. So the common ratio is 0.7. Okay. So then if we take this and plug it in, I think it's 15, right? Yep. So the sum of the first 15 terms here is going to be 5 times 1 minus 0.7 to the power of 15. Hopefully my counting is proper here. Over 1 minus 0.7. I think I'm gonna just use a calculator for that. Okay. So I have 5 parentheses 1 minus 0.7 to the power of 15. Okay, that closes off the numerator divided by 1 minus 0.7. Okay, that's okay. Okay, I think this is okay. This looks decent. Okay, we got approximately, let's go 16.59. Okay, we're gonna go with it for now, and then for part B. So let's see, the first term when I is 1, oh, this one's a little bit different. So when I is 1, what is that, 3.5? Because it's 35, right? Move the decimal to the left by 1. Okay. So then the first term in this case is going to be, looks like it's 3.5. Let me see, when I is 2, and it looks like the common ratio is still 0.7. So then the sum of the first, and I think it's still 15 terms. So I think everything is the same except for that first term. So we're going to say 3.5, 1 minus 0.7 to the power of 15 over 1 minus 0.7. Okay. So again, I'm just going to recall what I had before and change the 5 to a 3.5. So I want to insert 3.5. Okay. And I think everything else is the same. Okay. $11.61. Okay. All right. So we got 16.59 and 11.61. Let's see how do we do. 16.59, 11.61. Okay. Oh, we are just about out of time. We're almost there too. So the value of annuity, let P represent the payment in dollars made at the end of each n compounding periods per year, and let I be the annual interest rate. Then the value of A of the annuity after T years is given by this. So this is just a formula that we're going to use. P represents the payment in dollars, okay, made at the end of each compounding period. N of the number of compoundings. I is the annual interest rate, okay? And the annuity, okay? An individual retirement account, IRA, is a common way to save money to provide funds after retirement. Suppose you make payments of $1,200 into an IRA at the end of each year at an annual interest rate of 4.5% per year, compounded annually, okay? What is the value of this annuity after 35 years? All right, let me get a copy of this guy. I don't know. I don't know if I have the time. Let's try. So 35 years, okay? Let's go like this, like this. I really want to copy this. P. Okay. Let me cut this. Paste. Shrink it down. So we're just going to use this as a reference. I forgot my bar, but that's okay. This. Okay. So let's try to fill in the different components. An individual IRA is a common way to save. So the payment, so it looks like our P is $1,200, okay? The rate, so that's our interest rate is I. So usually 4.5%, usually that has to be as a decimal. So as a decimal, that's gonna be 0.045. Compounded annually, so that means our N is 1. And the time is 35 years, okay? So let's see if we can get it here. So then the value of this annuity, so if we just plug it in, 1,200, 1 plus 0.045 divided by 1, because it's 1 compounding per year. 1 times 35 is just going to be 35 there, minus 1, all over, let me make sure I'm doing this right. 0.045 over 1. It's nothing else. I feel like there should be something else, but we're going to go with it for now. And I'm going to just use this. I'm just going to use the calculator. Okay. All right. So for the top, first we got this 1 plus 0.045. Okay, that closes off, and we say that to the power of 35. Okay. And we're going to say that result minus 1, and then we want to close off the top. Okay, I think hopefully I got my parentheses correct. I'm going to say divided by, now the bottom, we got this 0.045. Okay, it's divided by 1, so it's just itself. And we get this result. Let me see. Maybe we did something wrong. 1 plus 0.045. I feel like we're missing something. One compounding per year. Oh, I see it. The 1,200, right? Okay, I see it. Yeah, the 1,200. So let me recall this. Come on. I need to insert right here 1,200, and I need to close all this off, right, like that. So I'll put parentheses around everything that we had before. Okay, that's what we were missing, because 81 didn't make sense, right? So at the 35 years, if we start with $1,200, wait a minute. Yeah. If you make, so every year you pay $1,200 into this annuity for 35 years, it looks like you have almost 100,000. 97,795. Okay, so we got approximately $97,795.94, right? Because that first result that we got didn't make sense. We got like 81. I was like, no, that doesn't make sense. Undo. Let me get rid of this. Okay. I'm just trying to box this guy. This style. Okay. So we got almost 100,000. Let's look at the prepared notes. Yeah, almost 100,000. 97,795, 94 cents. Okay. All right. So we only got a couple of slides. Let me just do a quick scan. The sum of the terms of infinite geometric sequence. So if the absolute value of your common ratio is less than 1, right? So if you have your common ratio, if the absolute value of that is less than 1, then the infinite sum, so if it goes on, if you add up the terms of a geometric sequence to infinity, when the common ratio is less than 1, it's going to collapse, right? Okay, I want you to look here real quick. Right, this one, right? So now, if this common ratio, if the absolute value of that is less than 1, as n runs to infinity, then this term goes to 0. Because when it's a number less than 1, basically it gets closer and closer and closer to 0. As n gets closer to infinity, this term gets closer and closer to 0. So then this summation collapses to a1 over 1 minus r, right? That's when the absolute value of r is less than 1. Thank you. Okay. So then that's where this comes from. That term cancels out. So then the last part is just an application of this. I'm going to have to leave that as an exercise because we are out of time. Okay. Anybody want to ask any questions? Okay. Let me share. So I'm going to send you a copy of what you saw me writing. This is College Algebra 2 into the note section. Updated daily right there. Week 11. Okay, when this bar finishes loading, you'll get a copy of what we just discussed. You know, if you don't have questions for me, there should be questions. I know everybody doesn't get it. When you don't ask questions, that means one or two things. Either you get it or you don't. You know, I can't do anything if you don't say anything. But hopefully you either have a trusted classmate that's getting it that you're working with, or you have a trusted tutor. Keep in mind that you have paid for tutors. The tutoring service is included in your tuition, so you definitely want to get your money's worth out of them. You don't want to just pay them money and then not use it. That's just throwing money away. If you want to throw money away, you're welcome to throw money my way. I don't take bribes. It's not going to change your grade, but I'm not going to turn around money either. Okay. But on that note, if there aren't any burning questions, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day, guys. Okay. Take care. Peace. Oh, wait, let's see. What's going on in the chat? Okay, geometric. So one question says that what makes something geometric? Geometric, so last time we talked about arithmetic where we were adding the same thing at each step. What makes it geometric is that we're multiplying the same thing at each step, right? So geometric means we're multiplying the same thing at each step. I know I saw another question. Let me get this student. See for the next class or this class. I don't know if somebody else had another question. Give me a second. He is here. Okay, I got him. What's the other thing? One other thing is that some students were concerned about how to improve their grade. As a blanket statement, if you are trying to improve your overall grade, my recommendation is just improve your exam scores. Where they count for 80% of your overall grade, that's going to be the most bang for your buck, right? So you get unlimited attempts, you can get it up to a 90%, after the fact. So yeah, if you're trying to improve your overall grade, you would definitely prioritize the exams. Again, that's the most bang for your buck. First is like the homework. The homework is going to be a whole bunch of work for a little bit of points, right? So I don't want you to stress out. Don't stress out too much about the homework. That's only like 10% of your overall grade. You don't want to put all this energy and not reap the fruits of your labor. So if you're trying to improve your grade, you can always go back and improve your exam scores because it's going to get factored into the final grade. And it's only going to show whatever your highest score is. Okay. All right, gentlemen. Until next time, take care. Peace.